Welcome to the video for Lecture 19, Section 1. This video brings together all of the previous process control material covered in this class. By the end of Lecture 19, we will have developed the overall transfer function for a water heater for both servo and regulator problems, and found the time-dependent response using the data given for the water heater problem. Section 1 covers the development of the transfer functions for each element and the closed-loop feedback control block diagram. This is the lecture that brings all the process control concepts we have covered before together. We will be able to solve fluid heating or cooling problems, liquid level problems, tank flow problems, and mixing problems. We'll be using closed loop feedback control, and we can add cascade or feed forward control. With the information given, we will write the transfer functions for each element listed here and combine them into an overall transfer function in the Laplace domain. Then we will use MATLAB to find the inverse and the time-dependent response, which we can plot using MATLAB. There are 7 steps to the process we will use. The first step is to write the transfer functions for each element in the closed-loop control system. For this course, we will use the equations and procedures we've developed and are in the course packet. You have different transfer functions for the process, sensor and feedback element, controller, and actuator. Occasionally there is a new part of the process that requires some development, so we will go through a couple of examples. The second step is to draw a block diagram. The diagram should be complete and indicate if the control system is feedback only, feedback plus cascade, or feedback plus feed forward control. The third step is to develop the overall transfer function using the technique shown with the non-interacting tanks in series. In many cases, we will develop the servo and regulator problems separately and then combine them together for the combined overall transfer function with a set point input function and an uncontrolled input function. In reality, you could have multiple uncontrolled input functions. The fourth step is to define the input functions for the servo problem when the set point changes and for the regulator problem when an uncontrolled input changes. This information needs to be given in the problem statement. There will also be other physical data that will need to be given to be able to find all of the element time constants. With the overall transfer function and other physical process data for each element, you will have a single overall transfer function in the Laplace domain. We will use MATLAB to find the coefficients and roots necessary to find the partial fraction expansion. The sixth step will be to take the inverse and find the time domain expression. The seventh and final step will be to plot the time-dependent solution using MATLAB. Here is the fluid heater problem we've used throughout the course. We assume that the tank is well mixed and well insulated to simplify the problem. The uncontrolled input we will use for this example will be the temperature of the cold liquid. We have a temperature sensor that is attached to a feedback element that supplies a measured temperature to the comparator. The error between the set point and the measured temperature is used by the controller to adjust an actuator that controls the amount of electric heat added to the cold fluid in the tank. Here is a generic block diagram. For this problem, we will assume that we are using feedback control only. We have a set point, comparator, controller, actuator, process, and sensor and feedback element. We write the block diagram in terms of transfer functions. Now we need to find the transfer functions. Here is a list of typical elements that we need transfer functions for to completely describe the feedback control system. This slide shows the original ordinary differential equation that we used to describe our fluid heater. For the fluid heater problem, we use the notation shown. Let me make a point here. In this course, you will not need to go back to the ordinary differential equation for these problems. I am doing this as a review. This slide reviews the possible uncontrolled inputs that could change for our fluid heater. The list includes the fluid inlet temperature, the fluid flow rate, and the set point temperature. We could allow all the inputs to vary and use a Taylor series expansion to adjust the equation because there would be a nonlinear term when both the inlet temperature and the inlet flow rate change. For this example, we will simplify the problem and assume that the fluid flow rate is constant and that the inlet fluid temperature is the only changing process input. We did this development back in Section 5 of the course packet. We wrote the differential equation and a steady state equation. We take the difference. Then we introduce deviation variables so that we could use Laplace transforms. Please note that there is a notation problem. The problem is that we are using capital T as the deviation variable and it is also the outlet fluid temperature. We take the Laplace transform and define the time constant of the fluid heater. Here is the Laplace domain expression and block diagram. Both relate the outlet fluid temperature T to the amount of electrical heat added Q and the inlet fluid temperature T subscript I. There is a problem with this block diagram. We do not want the process output to be the output of a summing element. All of the previous closed-loop block diagrams we've drawn have had the process output coming out of a common process transform. This was covered in section 12 of the course packet, page 12-3 to be specific. Here is the preferred way to write the transfer function and draw the block diagram so that the process output T comes out of the general transfer function. Here is the temperature sensor and feedback element transfer function. The development was in section 8 of the course packet. Here also is the time constant for a temperature sensor based on a lumped heat capacity analysis. Here is the transfer function and block diagram for the temperature sensor and feedback element. As we have done before, we will assume that we will use proportional control only. We go to section 14 of the course packet and find the appropriate transfer function, P over E equals Kp, for proportional control. Also shown is the block diagram of the controller with the comparator and the set point Tr. Here is the transfer function block diagram for a relay. The gain is given by Kv. The relay is used to control the amount of electrical heat added to our fluid heater. This slide shows the overall block diagram with the transfer functions we just went over. It is my hope that you can look at any part of this block diagram and any transfer function and know what it is and where it came from. Again, let me repeat that you will not need to develop all of the transfer equations. You can just find the appropriate transfer function and put it in the correct place in your block diagram, as we did for the feedback element, controller, and actuator. This is the block diagram for feedback control only. If the problem had cascade or feed forward, there would be additional elements. Now that we have the block diagram with all the transfer functions, we are ready to find the overall transfer function. Again, we will find the transfer functions for both the regulator and the servo problem, but we are going to do that in the next video. This brings me to the end of the Lecture 9 Section 1 video. Write down any questions you have and bring them up in class or lab.